Hi, I'm Melissa, an onboarding engineer at SkyCiv. Welcome back to our series on the Quick Design ACI 31819 Concrete Column Calculator. In this video, we'll be working through example 11-1 from Reinforced Concrete Mechanics and Design, 6th edition, to show how SkyCiv can help answer real-world design problems. Instead of manually following each calculation step from the handbook, I'll input the given parameters from the example into SkyCiv and show how the calculator can generate the necessary design checks and interaction diagram. Before we get started, let's quickly review why interaction diagrams are important in structural engineering. An interaction diagram helps determine the axial and bending moment capacity of a reinforced concrete column. It shows whether the column can safely withstand a given combination of axial and moment loads. Instead of manually calculating multiple points, software tools like SkyCiv generate the full diagram instantly, making the process more efficient. The example 11-1 reads, compute 4 points on the interaction diagram for the column shown in figure 11-17a. Let's start by reviewing the given data in the handbook example. The concrete strength is 5,000 psi, steel yield strength is 60,000 psi, the column dimensions are B equals 16 inches and H equals 16 inches. The longitudinal reinforcement is 4 number 9 bars on the top and 4 number 9 bars on the bottom according to this graphic. The cover and reinforcement placement as shown on the diagram is cover equals 2.5 inches. The example is defining the cover to the center of the bar, so we will make our cover 2.5 inches minus the number 9 bar diameter divided by 2, which will be 1.936 inches in our case. Now I'll enter these values into the SkyCiv Quick Design ACI 31819 Concrete Column Calculator under the following sections. Dimensions, I'll enter the width, depth, and column shape. We already have 16 inches by 16 inches. The flexural reinforcement, the cover will be 1.936, and the left and right reinforcement will go away. The top reinforcement and bottom reinforcement will have 4 bars on the top and bottom, number 9 bars. The shear reinforcement in the example is not specified in the graphics. I will leave them as number 3 bars, but it does look like they do have 2 ligatures in the y-axis. I will add those in as well. I am also going to make the reinforcement type other because in this example, we know that it is a tied column. The span is also not given in the example, so I will leave it as 80 inches. The concrete strength is 5,000 psi. And the steel strength is 60,000 psi. The design forces were not specified in the example, so I'll leave them as the default inputs. Each input corresponds directly to the values given in the example. Once all the values are entered, I'll click Run to generate the results. Now that we've run the calculator, we can see the output summary on the right and the detailed calculation report in the center. I've already downloaded a PDF report, so let's take a closer look in a new tab. Before we focus on the interaction diagram, let's quickly review some key sections of the report. The material properties. Here we see the concrete strength and yield strength we input earlier, as well as design forces. This confirms that the calculator is analyzing the exact loads provided. The member detailing and capacity checks. These are ACI 31819 code checks that ensure the column meets minimum reinforcement spacing and other detailing requirements. These automated calculations ensure that the design complies with code requirements while saving time on manual checks. Now let's compare SkyCiv's results to the values calculated in the example. The handbook first determines the axial load capacity. The book calculates PO to be 1,530 kips. SkyCiv also calculates PO using the same formula and getting an answer of 1,534 kips, the handbook rounded down. You can also see that the handbook uses a fee of 0.65, and so does SkyCiv because it is a tied column. We can then see that fee PN max was calculated to be 798 kips in the example, which also is calculated in SkyCiv as 797.7. Again, the example is rounding. Next, the example walks through several key points on the interaction diagram to determine the column's capacity at different strain conditions. Instead of manually calculating these values, SkyCiv generates the full interaction diagram summary showing pure compression capacity, balanced failure point, tension controlled failure point. This is a major advantage. The entire interaction curve is calculated instantly, whereas a manual approach requires checking each point separately. Let's take a closer look at the interaction diagram for unit axial bending about Z, generated by SkyCiv. The x-axis represents the bending moment capacity, while the y-axis represents the axial load capacity. The curve itself marks the boundary of safe design limits. Any load combination inside the curve is safe, while anything outside the curve is unsafe. The handbook example plots 4 different points along this diagram, each corresponding to a different strain condition. Balanced failure. This point occurs when compression and tension reinforcement yield simultaneously. Pure compression and tension failure, extreme ends of the diagram where the column fails entirely due to compression or tension. Compression, tension, transition points. These are intermediate points marking transitions between compression and tension controlled failure modes. SkyCiv automatically calculates and plots all of these points, allowing us to visually confirm whether the column meets ACI 31819 design standards. Now let's check where our applied design load falls on this diagram for bending about Z. In the handbook, the calculated axial moment capacities are plotted manually to verify that the design is safe. Again, this example didn't give an example design load, but for our factored axial load of 10 kips and the factored moment of 50 kip feet, you can see that in SkyCiv, the design load is automatically plotted, allowing for an instant check. Since the load falls inside the safe region, we can confirm that the column meets ACI 318-19 requirements. If the load had fallen outside of the curve, we would need to increase reinforcement, adjust column dimensions, or select a stronger concrete mix. Now I will scroll through. You can see that we have another interaction diagram for bending about Y. And the last interaction diagram for biaxial bending, considered in both Y and Z axes. Let's briefly explore what would happen if the column failed the interaction diagram check. Going back to our design inputs, if we reduce the column width or decrease the reinforcement, we can see how the interaction curve shrinks, reducing the safe load carrying capacity. Again, we can see how the interaction curve shrinks, reducing the load carrying capacity compared to our original interaction diagram. Similarly, increasing the concrete strength or adding more reinforcement expands the curve, making the column stronger. This feature allows engineers to iteratively adjust their design to ensure compliance. This example highlights how SkyCiv's quick design calculator automates complex engineering checks, saving time while ensuring compliance with ACI 31819. Instead of manually working through every equation, the software quickly generates axial and bending moment capacities, interaction diagrams, and detailed reports for verification. This makes it a valuable tool for engineers, educators, and students working with reinforced concrete column design. If you have any questions about using SkyCiv for reinforced concrete design, feel free to reach out via SkyCiv chat support. We typically respond within 30 minutes. Be sure to check out the other videos in this series, including a deep dive into the interaction diagram and an introductory walkthrough of this calculator. Thanks for watching, and I'll see you in the next one.